All right, so what did we do last time? Who remembers? I always feel like multivariate integrals. Okay, how do we manage? We looked at a rectangle and we looked at a circle. And what did we learn about from the circle?
Use polar coordinates.
You can use polar coordinates. That will make your life easier because the limits of the integral will be fixed values in that coordinate system. So we learned that the rectangle was much easier because the limits of the integral were natural in the Cartesian coordinate system, and then the circular one wasn't natural, but we started talking about how it would be natural and polar coordinates. So, and then we hinted at the fact that you have to do something fancy to convert the coordinates at the end. And then the one other thing we talked about was we talked about a lot of things that were like the integral of something d volume over something else d volume. How do we interpret those things?
Calculating the center of mass.
Yeah, so we can do this one is, so the integral of the density times the volume is going to be the mass, and this one is the volume. So this would be the density, which is the average density. But if we had put a vector in here, we could have calculated the average density times location, which would be the center of mass, and so on and so forth. So there are a lot of, I guess we could, down here, this would be the mass weighted center, so the center of mass, which is the density weighted location of the object. So, but this, in general, this kind of ratio of like, we do some complicated integral including an effect, and then we do some other complicated integral taking away the effect below, and we get the normalization right because all the limits are the same in the top and bottom, and so we don't have to worry about, it takes care of a lot of things just to think about averages like this. So we'll see that again when we get to Fourier transforms in a bit. Okay, so what do we have to do in multivariable integrals like this if we want to switch coordinate systems? So we talked about how it isn't as simple. So if I want to do the integral over a circle, we did some crazy thing where we had square root of, y squared minus r squared negative plus y squared minus r squared, and then we go from like x would go from minus r to r. So this is I'm calculating a circle, sitting at the center, x, y. We said last time it would have been easier if we had done it at the center, but we didn't do it at the center. But now I'm doing it at the center just to show you how it would go. So any point on this, we know that it would have r squared equals x squared plus y squared would be the formula for a point, right? So if I want to integrate the area of that circle, I would integrate something dx dy. If I'm thinking of the area, what is the thing that I'm integrating? Just one. Because this is already kind of area. So I would integrate one. If I wanted the mass of the circle, I might have density per unit area or something in there, or mass per unit area, or something like that. So it's possible to put other objects, but the formula for area goes like this. And we said that this is kind of a nightmare because we plug this, we do the y integral. We do the y integral first, and then we do the x integral, and it would involve a trig substitution, and we would all, that it would be no fun. But we knew, we suspected that the problem is that this function is so complicated because it's not a natural part of the coordinate system, and thus it makes the bounds of the integral some fancy function of the thing we're going to integrate over second. I'm just doing this. Maybe over x first, then over y. So when I integrate over x, my x's go away, but then my y's are surviving, and then I would integrate over y, and the y's would go away. And what's the answer? How big is the circle? The errors. You would expect that to be pi r squared somehow, even though it's not obvious at all when you look at this formula that it's going to end up being. Okay, so what if you want to do it in polar coordinates instead? So polar coordinates, you measure, it's like our, remember we had r e to the I theta equals x, or it equals r sine theta. Oops. This right. Cosine theta plus I times sine theta. And so if I want to write r's and thetas as a transfer from these little pieces, so if x is my real axis here, what's my formula for x? This is, if I'm thinking of this xy plane and also the complex plane that's the same one at the same time.
X equals R plus theta.
Yeah, so x equals, we're going to go from x and y, x equals r cosine theta, because this is the x term. And this is in polar coordinates, because it's got the r and the theta, we're not quite sure. And how do I read y? What's the y part of this? If this is the x part. If this is the x-axis is the real axis, real part of z. I call this z. And this is the imaginary part of z. So what's the imaginary part of z? Yeah.
Should it be IR something?
Yes. Even better. So now what's the correct?
IR.
There we go. So y equals r sine theta. Okay, so this is our conversion function from things that are written in x's and y's to things that are written in r's and thetas. And I could invert this as well and write it the other way. I could write r in terms of x and y. Right? And then I could write theta in terms of x and y, and I always forget what it is, but something like the arctan of x over y. Maybe y over x, I don't remember. Maybe. Alright, we'll use that formula for now. Okay, so if we want to integrate this sphere in a multivariate integral, we want to do a change of coordinates from x's and y's to r's and thetas. So we're still going to have two integrals. One of the integrals is going to be an r integral, and one of the integrals is going to be a theta integral. So what are the ranges going to be on those? What's the range on r and what's the range on theta?
The range for R will be from 0 to R.
R, right? So, yeah, maybe we should have capital R to distinguish it from the coordinate R. What about theta?
0 to 2 pi for this circle,
Because what?
because it's a circle.
It goes all the way around. Yeah. So it starts at 0 and it goes all the way around to 2 pi. So 0 to r and 0 to pi. Cool. And then we're going to need some kind of area element. What's our area element going to be? It's going to have a d theta, and it's going to have a dr. And we're going to be integrating 1 because we're still talking about area, but is that the whole show? Can't be. Why not?
what we showed last time is if you do actually integrate that, you don't equal to pi r squared, so you have to add an extra variable of r.
Yeah, so we need an extra something here that's r, and I'm going to claim that's the determinant of the Jacobian matrix of the transformation. Just because that's a lot of words. But I'll show you what that means in practice. It's not as complicated as that. Okay, now is this easy to integrate? Yeah, because it doesn't even depend on theta. So 0 to 2 pi is just multiplied by 2 pi. And then integrate an r, 1/2 r squared, plug in a big R, get the 1/2 2 pi equals pi r squared. Okay, so if we knew what we were doing, we would have done it this way instead of that crazy way, right off the bat. Okay, so what do I mean by the Jacobian of the transformation matrix? So the Jacobian matrix is a matrix built out of partial derivatives. So dx, dr, dy, dr, dx, d theta, dy, d theta. So what I'm doing is I'm taking all the coordinates on this side and just taking their partial derivatives with respect to the things on the other side. So everybody see how that is? And it doesn't, I always get confused about whether you go x, y, or r theta in this direction. It doesn't actually matter that much. The matrix, the transpose of the matrix and the matrix have the same determinant. And for now, the determinant is the only thing we need. Okay, so what's the determinant of a matrix like that? AB minus BC, right? And so look at what it's doing, is it's blending together the x derivative with r and the y derivative with theta versus the x derivative with theta and the y derivative with r. So it's kind of doing all the combinations and putting them together with a minus sign in the middle. And it doesn't matter too much why that needs to happen, but that's an important way to think about what this, it's encapsulating a little bit of information out of this. Last time we talked about it, it's like the area element in terms of dx's and dy's versus dr's and d thetas. This is the thing that helps you figure out what the conversion of the area element is. So what are these four pieces if I just wanted to calculate them? What's dx, dr? Cosine theta. What's dy, dr? Sine theta. What's dx, d theta?
Negative r sine.
Sine theta. And what's dy, d theta? R cosine theta. And I just was Googling this morning to make sure I had all the details right. And they did this one wrong. They had a minus sign there, but then they had another minus sign in the next step. So they got it right again. Okay. So how do we get so the determinant of the matrix is this guy times this guy minus this guy times this guy. So it's r times cosine squared plus sine squared. So can we simplify that more? We can, because what do we know? Exactly. So it's another way to put it is that this is like it's like the Pythagorean theorem sitting on that little triangle, but rescaled by the factor r. So that gives us r. So in this coordinate system, we do this little thing. It gives us r, and we stick it back in. We could have just looked this up, and that would have been fine. Polar coordinates are common, so are spherical coordinates.
Could you explain again why the Jacobian makes sense?
Oh yeah, why is that? So I didn't even say exactly. So what we're looking for is we're looking for a little element of area, which has like an element of x and an element of y in it. And I want to write an element of area that has an element of r in it and an element of theta in it. But it's sort of like doing all the partial derivatives of these relationships to get the conversion factor for this, because if we were careful about that, we would find in that transformation, plugging in these formulas, taking their derivatives, taking their partial derivatives, we find that the Jacobian sits right here.
Okay.
But even more informally, this thing has got to have length squared in it, and it doesn't until you put that piece there. And this thing has length squared in it, and an area element has length squared in it. So it's sort of like those things all fit together, units and dimensions wise. It'll be a little harder in the example I'm just about to do in a second when we do the Earth coordinates, because then we get like sines and cosines, and that would be harder to guess. Yeah.
So if we were trying to find the area of any shape, would we have to do the Jacobian to like find out what the missing piece here to stick that in?
Not necessarily. You could always do it this way. You just have to work hard on the integral.
Okay, but if
So-
we're converting it.
Yeah. So the reason why we did this, remember, was because we really liked the simplicity of having these not depend on any of the variables. Because one, we can do the integrals without worrying about the order, whether we do theta or r first. Two, it's just complicated, we'll use square roots and things, and that makes the integrals hard. After the first one, it starts getting nasty. But they're equivalent operations, so you can do it either way. And sometimes you get into systems where there is no natural coordinate system that's friendly to your problem, and then you just have to do it hard. So that happens. We're going to see when we get to the end of the class and have some of the PDEs under our belts that actually these coordinate systems arise from being the natural systems in which certain classes of physics work. So things like circles appear in like diffusion from a central point problem, and things like rectangles appear in sheets of propagation of lines from one direction or the other direction. So we're actually going to see that some of these things occur naturally in the problems, and we will come to find that the coordinate systems we're familiar with, they're about 15 or so that have all this stuff worked out for you. You could look up in a book that's fancy, like Abramowitz and Stegen is the fancy one that's like about this fat, and it's just like everything you want to know about these 15 coordinate systems and a lot of other integrals and things. They come because they're naturally related to some of the classic physics problems that happen. So the coordinate systems make those problems easy to solve, the same way that polar coordinates makes the area of a circle easy to calculate. Okay, so let's talk about the Earth one, which isn't one in Abramowitz and Stegen. It's sort of a manipulated version of spherical coordinates. So we don't know what the answer is right off the bat, but we can go through it again. So what did we say? Remember we had this idea yesterday where we had the Earth, and here we are sitting in our little box. It's our classroom. It's a tangent plane, more or less north, east, up in terms of the combination of gravity and the Coriolis force is down. So, okay. So if I was going to write a coordinate system, you ever forget how to write cursive? Okay, I want to write it that way. I don't remember how to write a Z. I can see it on the page, but I don't think I can make my hand do it. All right, there we go. Okay, so I claim that those things are what we talked about, with this Z being our local vertical distance from the radius of the Earth. These are all radii of the Earth. Okay, so here's Z. Here's the radius of the Earth. Where's everything else? What's theta and phi? I'm thinking of this, I guess, relative to a big coordinate system. X. Oh man. Sorry. I drew us in the wrong part of the planet. We're over here. Because I want to draw an X that comes out, a line that goes back that way, and a Z that goes that way. This is our little z. This is our radius of the Earth. Okay. And here's a hint. Here's the Atlantic Ocean. So, what's X aligned with?
0 degrees longitude.
Yeah, so 0 degrees of longitude. So here, there's South Africa and there's the Greenwich Observatory on that line, right? So that's the 0 line for longitude. So which one of these then is longitude? It's phi, which I've chosen because this straight line looks like a line of constant longitude. It's like drawing a little line of longitude. Okay? So cosine theta then is latitude. So phi is measured going around this way. Where is theta measured from?
X to Z or Z down to X?
Yeah. So how can we figure out which one it is? Let's look at this one. This is the simplest one because it has only this guy in it. So when is script Z in the same direction as Roman Z? Theta is 90 degrees. And it would be negative when theta is minus 90 degrees. So is this, what is this? What goes from plus 90 to minus 90 from the North Pole to the South Pole? The latitude. Okay, so it shouldn't be that. So the latitude, this one, is the latitude. So, sorry, I drew it wrong. From the equator up, this one is the latitude. Okay, so this is what we're used to in that sense. Okay, this is just local vertical z. This is latitude, this is longitude. Hey, look, it looks like a band of latitude. It looks like a band of longitude. So the symbols are matching our stripes that we would draw. So none of this is surprising except for the fact that this is not what people normally use for spherical coordinates. For spherical coordinates, they normally use our distance from the center of the Earth. And yesterday we mentioned it would be weird to say 63,070 kilometers in 1 meter. So we measure relative to some local level in the vertical, which we just call the radius of the Earth, and observe it away. And then also frequently people, particularly in physics, like to use the co-latitude rather than the latitude. The co-latitude is the one that starts up here and goes from 0 to pi. So why they've done that, I don't know. They're totally obsessed. Well, I do know, but I'm not going to, it's not an important thing. The point is when we write in latitude and longitude, what happens is that this is either a sine or a cosine, and this is the opposite one. So we'll actually get a slightly different answer for our Jacobian than we would if we did the standard spherical coordinates that have co-latitude rather than latitude. Okay? So let's do our Jacobian for this. So now we have a 3D Jacobian matrix. dx, dy, dz, dx, dx, dy, dz. Taking the determinant of that, and all these, delta, 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 delta. This is the way I used to do when you got in trouble in elementary school and you had to write sentences, I would always do them like this, which meant that I didn't understand what I was writing. Not with what the teacher had in mind. Okay. So what are our three coordinates? We've got longitude, latitude, and script z. Oh, I just did that backwards. See, that's what I was saying last time. Perhaps there's much struggle with writing script z that's killing me. Okay. So what's dx d phi? Z plus RE d phi cosine minus sine cosine theta dy d phi dy d phi. So now we got z plus RE cosine theta. Oh wait, no, I had sine theta. Now I've got cosine theta, that's right. Cosine phi, cosine theta. And then the other one is going to be dz d phi, so 0. Everybody see what I'm doing? And so I could continue on and take all those, and then I form the determinant of the 3D matrix, which is a little more complicated. So it's this one plus this one plus this one minus this one minus this one minus this one. It's a more elaborate pattern, each involving 3 things. But you work all of it out, and you get squared cosine theta. So if I wanted to do the spherical volume integral, I would have to have this conversion factor in my to go from integrating over dx, dy, dc, integrate with z plus re squared d curly z d phi, cosine theta d curly z d phi d theta. Okay. So could you have guessed this? Could you have guessed it based on units? Sort of. We knew we need some lengths because this is an angle and this is an angle. So we needed to depend on length squared, whatever it was, and it does. And maybe it's obvious that it should be the combination of the local z plus the radius of the Earth. You could think of it, it doesn't really appear anywhere else except for in that combination. So maybe that's obvious. But the cosine of latitude is really funny. Do you think of an intuition for why the cosine of latitude is there? Try and draw it on top of it. If I take a box that's between 2 meridians, so between 2 lines of constant longitude, down at the equator, and up near the pole, what percentage should be the same height? So I claim that those two areas have the same width in latitude, longitude, and the same height in latitude. So they have the same number of degrees in latitude, I can measure with my fingers, and they have the same width in terms of longitude, but the longitude lines have gotten close together at the top. So everybody see why that is? And if you did it right on top of the pole, it would be infinitely thin. And if you did it right at the equator, it would be as wide as it would get. So cosine.
Above,
Yeah.
it's like similar triangles going up. So that's
So the cosine is that factor. Cosine is wide at the equator of latitude, and it's narrow at the pole. So the cosine is telling you that an element of area here is wider than an element of area there by some scale factor that depends on latitude, and the scale factor is a cosine. That makes sense to everybody, sort of? So this is where the infamous expression latitude is fatitude comes from, because the area elements are fat at the equator and they're thin at the poles. Okay, so if we didn't have that, and we were thinking of just little elements of area d phi, d theta, they would all be the same size, but they're not the same size. They have a correction factor that goes like cosine of latitude. Okay? Yeah.
Question. So the theta here is just going from the z to the equator? When it's
Yeah, so it's positive and negative. It goes from 90 degrees north to 90 degrees south.
Like that?
Negative 90, yeah.
oh, so it's going like
So it's latitude.
It is from 0 to pi.
It's from 0 to pi over 2,
Okay.
or from
And-
0 to minus pi over 2
Okay.
in the other direction.
Okay.
Or 90 degrees north, 90 degrees south, or minus 90 degrees north is maybe the way to think of it. Yeah. That makes sense, everybody? Okay. So we've been working hard on integrals, and before we were working hard on partial derivatives. So what was our killer application that we used for partial derivatives? What was the thing that was motivating us, or the thing that we wrote down that involved like really crazy partial derivatives, where we were like, we're going to need this later? Right, remember?
The multivariate Taylor series.
Multivariate Taylor series. So now we'd like to write down the multivariate Fourier series. And in order to do the multivariate Fourier series, we need to know how to do multivariate integrals. So we're going to talk more about Fourier series than we did before. That's going to be the rest of today and then the next time. And we'll see that if we did Fourier transform in x and y, we would need exactly this kind of integral to evaluate. But if it was something that was isotropic, the word means doesn't depend on angle, and it was sort of like ring-shaped surfaces of symmetry from the origin, then we might prefer to do an integral for Fourier transform that's in r and theta. So this is exactly the kind of framing that we would need to think about multivariate Fourier transforms. Okay? And so both of those are driving forces. Why are we interested in Fourier transforms in Taylor series? Because they're approximations, because they help us describe uncertainty, and based on the level of complexity of the approximation, and because they're based on linear constructions. So all of those three things will make them very powerful when we go to do solution techniques based on either Fourier transforms or Taylor series of differential equations, we'll be able to use those ingredients in a really powerful way so that we can just pull apart the differential equations and look at solutions that are nearby a particular set of XYZ times, if we're using the Taylor series, or as a function of scale, big things versus little things in Fourier series. And that will be a really powerful way to start diagnosing what all the different terms in the equations mean when we get to them. Does that make sense a little bit? Okay, so let's talk about Fourier transforms. Or not Fourier transforms, Fourier series first, and then Fourier transforms in the end. Or even before that, we're going to do a bunch of integrals, sines, integrals. Fun. Okay, so. So we talked about thinking about things being the average, being an integral of something over the integral of something else. 1 over, whatever, we talked about it being that way. So a Fourier series can be thought of a little bit like that. If I have a function, whatever it is, and I'm trying to approximate it with sines and cosines, what I'm looking for, time, function of time, from plus pi to minus pi. I'm sorry, this is just convenient to do it from pi to pi for now. It'll make all of our limits simpler. We will quickly get on to using this for arbitrary lengths. This is just like whatever our collection unit of time is, we're going to assume everything's periodic from minus pi to pi. And so our function just repeats again and again and again, over and over again. And when we take our Fourier series, it's going to approximate those bits. So what the Fourier series is I want to match the area under here, and the area under here, as close as I can to the equivalent areas under my function. I want the average value of the function as expressed in terms of a matched value of that sine or cosine to be set up the same way. I know that's sort of funny for now. But let's start thinking about how would I get the area underneath that curve? I would integrate. So I would have something like f of t dt, and what would the bounds of my integral be? To get this whole window? Negative pi to pi. And if I was going to normalize it by something underneath, because I wanted the average value of f of t, what would I put down below? I would have 2 pi, or the integral from minus pi to pi, or 1 dt, which is just equal to 2 pi. Okay, everybody on board with all those pieces? So let's think about some functions we might be interested in integrating. Here we have 1. Here's the integral from minus pi to pi of 1, which is 2 pi, or the average of 1 is 1. Everybody got what I mean by that? So if I plugged in 1 up here and I had 1 down there, I would get 2 pi over 2 pi, I'd get 1. I have 1. What's the average of cosine of any integer times x? Let's do it step by step. What's the integral of cosine?
over whatever n sine is.
1 over n sine of nx, good. And I need to evaluate it at minus pi and pi over 2 pi. Just back downstairs. Okay, so what's sine of nx at pi? It's 0 for any integer n. And what's sine of nx at minus pi? Also 0. This one's 0. Interesting. Okay, let's play the other game with sine of nx. So now we got 1 over n is a minus cosine of nx. Pi minus pi over 2 pi. Okay, what's cosine of nx at pi? All right, let's do it first. What's cosine of pi? And then equals 1. 1. What's cosine minus pi? Also negative. What's cosine of 2x at pi? Cosine of 2 pi, positive 1. Cosine of minus 2 pi, positive 1. 3, minus 1, minus 1. So it's going to be minus 1 to the n over n minus 1 to the n over 2 pi, also 0. Okay, so this is interesting because I said what we're trying to do is match the average value underneath the sines or cosines. The average value underneath the sines and cosines is 0. Except for the one exceptional case, which is the cosine where n equals 0, which is this one. Okay? So it's a little weird. All of our functions have no average underneath, but we can think of the correlation of the function and that cosine. And that might have some positive flag. So what if the function tends to be up over here and then tends to be down over here? It might also have an average that's 0, but the product of those two wouldn't be 0. It would sum up to something not 0. Does that make sense to everybody? Because if I take the positive area times the positive area under the function, and the negative area times the negative area under the function, I'd get a positive overall. So what that breaks down to is thinking of things like cosine squared of nx and sine squared of nx, which, if you go through the same procedure, this is 1/2 unless n equals 0, in which case, this then implies it's 1. And this is 1/2 unless n equals 0, in which case it's 0. I can do this a little bit faster rather than doing the integrals. If I think about cosine squared nx plus sine squared. So what's cosine squared plus sine squared? It's just 1, always. And if I was going to draw the sine on here, the sine would look like this. And the cosine would look like this. They're just the same thing, just shifted. Right? So the average of cosine squared has to be the same as the average of sine squared if n is not equal to 0. Like they kind of have to be half and half of that 1. Does everybody see what I mean? Because all they are is they're just shifted to each other, but if I'm averaging from minus pi to pi of their squared, they have the same. They're just shifted. So that almost immediately implies those results. So rather than doing the complicated integral of cosine squared, which is not terribly complicated, but it's complicated, you can intuit the average value just this way. Did I use something special about the average in order to do that? Just as a parting shot before we go away. It's a linear operator because I distributed it over into the two different parts that make up the whole. Yes, so the average is a linear operator because it's constructed from integrals, which are also linear operators. We're